Thank you, Aaron, and thank you everybody for coming. I think that this talk will be a bit of a change of pace from some of the talks we've had in the last week or two. Because I think I've got one equation, but mostly I'm going to show you some observational results. And I'm basically going to talk about the changes in the properties of helioseismic modes that you get with solar activity. And I'll sort of work through them systematically, the frequency shifts going from low degree to high degree, and say also a bit about changes in the mode amplitude and the width. Just to give you an idea of what we're talking about, this is a sample, small segment from a bison spectrum. This is actually the whole 45 years of bison data, heavily smoothed and with the model fitted to it. So this is just one L equals 1, L equals 3 mode pair. And what you can see from that is that these peaks are not delta functions. There's more information in there than just a frequency. That you can measure the width and the amplitude and the rotational splitting, which we're not going to talk about today. And in fact, if you look closely, you can see that peak is not completely symmetric. It's sort of steeper on the higher frequency side than the low frequency side. So you can also measure the asymmetry, which I'm also not going to talk about that. And very often we just fit these things to the random series. And I say we've got 45 years of bison data. That gives you an idea that we've been collecting these observations for, well, basically 4 solar cycles now. So we've got quite a lot of data to go at that. And quite early on, okay, that's just to give you an idea of how the frequency, how the width of the modes varies with frequency, and so you have this sort of mostly increasing with about a plateau in the middle of the spectrum. That's the general shape, and then the amplitude peaks at about a 5-minute period, which is why we call it the 5-minute spectrum. Right, so from very early on, it became obvious that it was detectable that the frequencies weren't quite constant, but were changing by a small amount over the solar cycle. So this measurement on the left is from the ACRIM measurement, which was basically a solar radiometer, but the measurements were high cadence enough that they could actually do low degree helioseismology with it. So from the peak of one cycle, you've got frequencies up here, and then the instrument broke, and a few years later they fixed it, and then they were in solar minimum, and the frequencies were noticeably, significantly lower, and the difference is about half a microhertz between maximum and minimum for low degree modes. So that was interesting, but because the instrument had broken in the middle, it was also slightly suspicious. And then there's these measurements from the instrument in Tenerife, which became part of the bison network. And there you can see, sort of the whole solar cycle going up and down. And then we did the same thing with the sort of early parts of the bison network. So, I mean, that was published in Nature, and you can see that it's, it sort of looks reasonably convincing, but it's not, it's quite noisy. But, by the time you've got 3 cycles on board, you can really start to see that these frequencies are following the activity quite closely. And that's the last 3 cycles. So you know, there's definitely correlations, and what those curves are fit to different activity proxies. And what you can see is that if you fit it very nicely to cycle 22, then it doesn't fit quite as well to the other cycles. And that is perhaps telling us something, that the sensitivity of the shift, of the frequency shift to a given activity proxy may be slightly different in different cycles. And that could be interesting, because that might be telling us that the properties of the outer layers of the sun that what mostly affect these frequency shifts are slightly different in different cycles. Now, within a few years, we could measure the frequencies for long enough that we could actually get the sensitivity of individual modes to the activity. And you can see in this plot, which is also from Bison data from 1994, that there is basically, as you go up in frequency, the mode frequencies change more. And they're still very small changes. And we're talking about half a microhertz in 3,000 microhertz. So not much more than a part in 10 to the 4. So you really need to measure these things quite carefully, but it's a pretty robust result at this point. And that shape of the curve tells you that the frequency shifts are basically scaling with the inverse mode inertia. And the mode inertia is this thing, and this is the only equation I'm going to show you. But so this is basically a measure of the displacements of the waves, and the displacement is biggest near the surface, as you can see if you look at the eigenfunctions. So basically, if you get something that just depends on frequency in this form, it's telling you that most of the effect is coming from close to the surface and not from deeper inside the sun. And it's understandable that the modes are most sensitive to the near surface changes, because that's where they spend most of their time, because near the surface they're moving slower. So this is just going back to the idea that different cycles may not be quite the same. And this is fairly recent work, and we're just plotting frequencies against different activity proxies of the 10.7 centimeter flux, the sunspot number, and the calcium K index, and the different colors of different cycles. And you can see that maybe the sensitivity isn't quite the same. And looking at the same thing, this is for putting medium degree data and Bison data together over 3 cycles in different frequency bands. And there's some indication that in this cycle 22, the low degree modes seem to have been a bit more sensitive. But at sort of higher frequencies, in cycle 24 is a bit more sensitive. And that sort of makes sense if you think about the layer that affects the mode frequencies getting a little bit more squashed, because the different modes have slightly different upper turning points as well as different lower turning points. And so some of them may, if that layer is thicker, then they're affected more. And if it gets squashed, then those sort of fall out of being affected at all at the lower frequency end. So that's sort of one, sort of interesting ongoing thing, is how different are different cycles in this, in the way they affect frequencies. Now, moving on from the bison data to look at modes that are measured with imaging instruments like GONG and MDI and HMI. And actually this plot here is a very old one, which predates all of those. This is from the Big Bear observations in the 1980s. And so the upper curve is near solar maximum. The lower one is about halfway up the cycle, and it's a difference from solar minimum in averaged frequencies over a range of degrees. And you can see very clearly that that shape that's characteristic of the mode inertia dependence. And I sort of came along a cycle later and plotted the corresponding results from GONG on top. And I think when I originally made this slide, it was an actual overhead, I was actually overlaying physical pieces of overhead transparency. And this was a couple of years before the solar physics community discovered PowerPoint. Very old graphic. Here, that shows the frequency shift per unit activity and color-coded by the degree. And so those are the raw values, and here it's scaled by the inverse mode inertia, which sort of collapses it into a curve, but you can see that it's still not flat. There's a frequency dependence to it. And that frequency dependence, in fact, you can parameterize. And it sort of basically, mostly it goes like the cube of the frequency. With possibly some helps to put in an inverse frequency term as well. And so basically it behaves very much like the surface term, which is the thing that you have to use when you're comparing frequencies with model predictions. As you go up in frequency, the agreement gets worse and worse. You can take care of most of that with a frequency dependent term if you don't want to get clever. So there's the frequency changes. And also, I mean, the beauty of having resolved sun measurements is that you can see the azimuthal degree dependence of things, which means that you can see the effect on modes that are sampling different latitude ranges of the sun. So we have these, what we call the even A coefficients, which are if you use a coefficient expansion of all the modes of the same degree and radial order and different azimuthal order, the odd components of that expansion tell you about the rotation, but the even coefficients tell you about the asphericity, which is quite a small effect, but it's very definitely there. And the different order coefficients have a very clear variation with time, which I mean, you can barely see, but under those points, there's actually a dashed line which is fitted to the corresponding order of the components of a Legendre decomposition of the magnetic field distribution. So basically that's telling you that the geometry of what's driving the frequency changes is following the geometry of the magnetic field distribution in latitude, which sort of evolves over time during the solar cycle. And I mean, that's basically the same plot, but brought somewhat more up to date. And so about 2 cycles worth of it. And you can see that holds up very well. In fact, you can take this a step further and do a kind of inversion in latitude to localize where the frequency shift is actually at. And it turns out that, surprise, surprise, it's exactly where the magnetic fields are. So here's sort of a butterfly diagram from the first 6 years or so of GONG observations. It's sort of symmetric about the equator. So you can basically ignore the bottom half, it's just a reflection of the top half. But you can see that the frequency shifts when you localize them like this map extremely well to the activity distribution. And that's a very recent update of exactly the same analysis. And I got a little bit better at doing plots since then. So we have the frequency shift following activity there we're at a sort of time scale of a few months and a latitude resolution of a few degrees. And then if you go to local helioseismology and ring diagrams, which as Aaron was describing in his lecture, you can take a small patch of the sun and look at the spectrum in just that portion. And you can measure the flows, and also you can measure the structure. Well, you can measure the frequencies, and those change with activity as well. And as Brad Heinemann and collaborators showed, you can actually see an active region moving across the disk from day to day in the frequency shifts, which is a very beautiful result. You know, it shouldn't be entirely surprising given what we've built up so far, but it's nice to confirm that this hold even at these, you know, sort of scales of a day, time scales of a day, and spatial resolution of about 15 degrees in this case. And Rajaguru et al. Looked at some comparing active regions with quiet regions and showed that the frequency dependence in the frequency shifts for local helioseismology is there as well. You can see the sensitivity increasing with frequency. But I mean, that's just an increase. But if you go a bit higher in frequency, which you can do if you take a large enough patch, that you can measure the frequencies to up beyond the acoustic cutoff, and things start to get interesting. And on the right hand side, we have basically a synoptic chart of frequency shifts for one Carrington rotation. And on the right hand side, there's a scattered plot of frequency against activity and magnetic activity index. And you can see, you know, to a point, they're just increasing. But then you get to a point where it's more or less flattened out. And then at high frequency modes, we actually got an anti-correlation. And then it turns around again. And there we've got something that on the scatter plot doesn't look very correlated at all. But if you look at the map, you can see that there's a sort of weaker anti-correlation there. But so what if you sort of fit a function to these things and look at the coefficient, you know, the linear coefficient of that fit, what you get is you can see the increase in activity, which we're familiar with. And then when you get to the acoustic cutoff, it sort of dips and goes down very steeply. So you get these modes quite strongly anti-correlated, and then it comes up again. And in fact, you can do even better than that. That's from Gong data, which was my late colleague Irene Gonzalez Hernandez did that analysis on some bison data with 30-degree patches. But HMI, you get the 30-degree patches out of the pipeline, and they return frequencies up to very high ranges, and then you can see it going up and down and up and down again, and so it's changed sign again down here. And if you look at the scatter plots, you can see that these things are not always monotonic. There it sort of goes down steeply at low activity and then goes up at higher activity. So I think that basically what these slopes are telling you is that you're sort of sampling a different, you're sort of trying to fit something that doesn't really fit. So just trying to fit a straight line to that, and it doesn't go. But what comes out of this is that over time, if you look at these along the solar cycle, the frequency at which that coefficient of sensitivity changes sign actually varies with the solar cycle. You can see that these contours, which are the zero crossings, are not straight. And in fact, they are following the activity very closely. And this is not only seen in ring diagrams. This plot down here is from analysis by Androde and collaborators of high degree global modes over short periods. And you can see the same kind of behavior, but also you can see that it's at different times of the cycle, it's sort of crossing the zero at slightly different places. And what that is telling you about is, when you think about what the acoustic cutoff means, it means that there's a frequency at which the modes are no longer trapped, but they're sort of going out into the atmosphere. And what seems to be happening is that for some modes that are kind of on the borderline, depending on how much activity they're encountering, they may be trapped when you wouldn't expect them to be. So exactly how the frequency at which the modes are trapped changes with the solar cycle is what that seems to be telling us. Now, so take a little breath here. That plot may look rather similar to the other plots I've just been showing you, but it's completely different. If you look at the axis, this is now, we're plotting a change in a quantity called the acoustic radius as a function of the fractional radius in the sun. So what this is an analysis by Sasha Kosovichev and colleagues. So what they're saying is that there's something about the cavity is changing, and they've got some resolution on it, but it's only in the outer layer. So there's kind of two-layer structure in the response of the modes. So, I mean, this is now moving into the part of the talk where I tell you about what might be changing under the surface, having established what's changing at and above the surface. Now, here, you can measure, given the frequencies of the modes, there's the helium ionization zone makes a sort of boundary, which causes an oscillation in some combination of the frequencies, fourth difference. And the amplitude of that signature tells you how strong that glitch is. And that apparently has been measured, and that seems to change with solar cycle. This is measured in Gong and MDI, and this is measured in Bison. And this is a more recent updated measurement, again by Sabani Basu and student. So you can see that there is an effect of the frequency changes in the shallow outer layers, but not completely. It's not absolutely superficial. There's something going on a few % down into the convection zone. What we'd really like to know is whether we can detect signatures of fields, really deep down in the convection zone where the dynamos, by some accounts, happen. Now, this is some measurements using Gong and MDI data, and you can see that maybe something changed sort of near the bottom of the convection zone, this kind of glitch. But in solar maximum. So maybe there's something there, but it's not particularly easy to understand. And this measurement from Bullner and Basu is looking at sound speed changes near the base of the convection zone. And the error bars are big, but you can see that, sort of depending exactly where you are in relation to the bottom of the convection zone, that's sort of 0.7, well, it's 0.71, so that's just above the bottom of the convection zone. That's down, and that's sort of below the bottom of the convection zone. The change, what looks like a change in the sound speed. That's sort of below 45 degrees latitude. So they may just about be able to pick something up. And finally, this is an extremely recent paper, which only just popped up on the archive yesterday. And if it had cropped up a few days earlier, I might have picked it for my journal club presentation. Well, possibly not, seeing as Saban is on the SOC. Anyway, so here they are again looking at sound speed changes at the base of the convection zone. Well, once they noticed something, that if you, even though I sort of pointed out that most of the effect of the frequency changes look very much like a surface term that changes. They did notice that, in fact, if you do that kind of fit, the chi-squared changes with the solar cycle. So they believe that there's something there, and you can in fact see what looks like quite a significant change in the sound speed at the bottom of the convection zone at different depths over time and as a function of activity index. That's from MDI and HMI, and that's from Gong, which is sort of looked a bit more convincing because it's oversampled, but they carefully didn't use the oversample data for the scatter plot there. Yeah, that was quite good. So that's promising work, I think, that shows that maybe you can detect some change in the sound speeds with the solar cycle below the, at the bottom of the convection zone, not just at the surface. Right, so that's frequencies. Now, I'm not going to go into quite so much detail about the changes in the other properties of the modes, but it is possible, as you get more measurements, to measure the amplitude of the modes and also their line width over time. Now, the first time we tried doing this with Bison data, we could see a very clear anti-correlation with solar activity for the amplitude of the modes, but really couldn't see much at all in the line widths. And the line widths are the more difficult thing to measure, particularly with somewhat sparse ground-based measurements. The line width is very sensitive to the duty cycle. And basically, if the measurements are only half there, then the power in the mode gets spread out over more frequencies than you would expect. So you have to be very careful to correct for those effects. And we were a little unlucky in the early years that the Bison duty cycle was very bad in the solar minimum and got better as we went up into the maximum of cycle 22. So we had to be extremely careful about interpreting those measurements. And it took, I think I spent about 3 years trying to make this effect go away before we finally published it. And then a few years later, Bill Chaplin was able to show that in fact there is a small effect in the line in the line widths as well. And the line widths, if you remember how these things work, that the line width is inversely related to the lifetime of the mode. So the shorter the lifetime of the mode, the wider the peak that it shows up. So you can just about see as a function of frequency that the line width is correlated with the power, and more so in the middle of the spectrum, and the amplitude is anti-correlated. And the mode supply rate, the energy supply rate, those two effects more or less cancel out. So the conclusion was that the effect on the modes and amplitude, the line widths and amplitude is basically an effect of the damping changing due to magnetic activity, and not the excitation of the modes. But there is a caveat to that, which we'll come to presently. So, you know, so move on a few years, and you can fairly clearly see the line width increasing with activity in low degree modes from various sources, sort of measuring both the Bison spectrum, which is a low degree spectrum, sun as a star, and also taking the 0 degree spectra from GONG and MDI, and they're all doing the same kind of thing. And the amplitude decreasing with activity, going up to the maximum cycle 23. And here, Kiefer et al. Looking at 2 cycles worth of GONG data, and we can see amplitude, line width changing. But the measurements, the whole caveat was having to correct very carefully for the duty cycle applies in spades to GONG data. But there's a fairly convincing effect there, and the anti-correlation of amplitude. And also, at least over a relatively short period when the instrumentation was fairly stable, it's possible to do the same thing with the same trick with localizing the data. You can do this with GONG because they actually fit each component individually and get an independent line width for each mode, which the fitting for HMI and MDI doesn't do. And so we put that through the same kind of 1D inversion technique that we did for the frequencies, and yes, you can see that it maps very nicely to the butterfly diagram. And that's the same thing for the line widths. So that works. You can see that the you're having effects that are spatially correlated as well as temporally correlated with the activity. And you can extend that to ring diagrams too. Now, when you're measuring a ring spectrum, you're really measuring the width of a ridge which has a lot of modes in it. So exactly what the line width means at that point is a little bit complicated, but it's sort of definitely correlated with the activity. And so here we can see, again, this is Carrington rotation 1988, which got exhaustively studied because it was the first one that we had good GONG data for, and also matched. We had MDI data at the same time. So we did a lot of work on comparing these. So you can see that the frequency is increasing where the activity is, and the power is decreasing, and the amplitude and the line width is increasing. But then if you look at a very high frequency mode, this one's around the acoustic cutoff, you can see then that the amplitude has actually gone up in the active regions, and the line width has gone down. And there I've sort of plotted that's for the amplitude, and you can see the sensitivity as a function of frequency. And the sign change actually there happens a bit before the acoustic cutoff, not out. So it's not completely related to where the frequency change goes. And that's just a quadratic term. I thought when I picked this plot that was the amplitude, but then I realized it's not, it's the, this was the line width, it's not, it's the right, this is line width because it's positive in the middle of the spectrum, and that's the quadratic term in the expansion. So that's giving you an idea that the amplitudes and line width and lifetimes of the modes are affected by magnetic activity. So the activity is basically damping the modes more, which makes the amplitudes lower and the lifetime shorter. And then just for one last example, it's not only these quantities that change. Here we were looking at basically nu max, which is a property that people measure for stars, the sort of peak frequency of the spectrum. And this is sort of various estimates, so it's based on various sums of star observables. And you can see that it's weakly correlated with the activity over a couple of cycles. So, and it's not a very big effect, and the effect of looking at different observables is bigger, which, is just sort of caution that, sort of not to treat the nu max as a completely fundamental parameter, because it does depend what observable you're using, and to a minor extent it depends on how active the star you're looking at is at the time. So be very careful when comparing nu max measurements from different sources, I think is a bottom line from that. So to sum up, we can say that the frequencies and the widths and the amplitudes and some other properties of helioseismic modes vary with solar activity over a wide range of temporal and spatial scales. And this can tell you things about the properties of the outer layers and atmosphere of the sun. And it gets really complicated when you get into the modes that aren't always trapped. And if you look at it over multiple cycles, you can get some sense of what's going on with the magnetic properties of the outer layers of the sun. And there are hints that we can detect changes deep inside the convection zone, but that's still quite a difficult measurement to do. And when you see strong signals in the frequency changes, you have to remember that almost all of that is coming from very close to the surface. And so basically that's what I wanted to say. Thank you very much.